We continue our review of the limit techniques in calculus by talking now about infinite limits. We're first going to start by looking at a particular function, namely f of x is 1 over x. Of course, the domain of this particular function is the set of all real numbers minus the value that makes the denominator 0, namely the set containing the value of 0. We would like to focus on the behavior near this value of 0, and that's going to be given to us by looking at the limit as x approaches 0 of this particular function. So let's try to first look at the graph, and we'll notice that to the left and to the right of 0 there's a very different behavior. Namely, if I start by looking to the left of 0, so as x approaches 0 from the left, we want to observe what happens with the function values f of x. Well, if I approach 0 through values from the left, then we notice that the corresponding y values, as I travel on this particular curve in the direction, the corresponding y values are approaching negative infinity. On the other hand, if I now look at values to the right of 0, and I want to notice for this particular x value what happens with the corresponding y value, I travel on this curve and I notice that the function values are shooting up to positive infinity. So we would like to record this in limit notation. So we write that the limit as x approaches 0 from the left of 1 over x is, based on this graph, negative infinity, which is a correct graph, and the limit as x approaches 0 from the right of 1 over x equals to positive infinity. We notice that in essence the function is not defined at x equals to 0. We have that f of 0 is undefined, but the behavior of the function near 0, namely to the left and to the right of 0, gives us this explosion to plus or minus infinity. We have in essence a so-called vertical asymptote. So we notice that the graph of the function explodes to plus or minus infinity by approaching, getting closer and closer to this particular vertical asymptote, and we record its equation of the vertical asymptote as x equals to 0. So when we look at this particular travel on the vertical asymptote on this particular line, we notice that the x-coordinate is fixed while the y-coordinate, the height, can vary. Therefore, we record that the fixed coordinate x is fixed at the value of 0, and that becomes the equation of the vertical asymptote. It's going to be very useful for us to have a shorthand notation for this particular limit. So we're going to abuse notation and write down that 1 over 0 from the left, and again by this we simply mean the limit as x approaches 0 from the left of 1 over x. This equals to negative infinity. And we're going to have the notation again that 1 over 0 from the right, namely the limit as x approaches 0 from the right of 1 over x equals to positive infinity. And these are two short forms that we're going to find very, very useful when we compute many limits. But in some sense, it's easier to remember that division by 0 produces an explosion to plus or minus infinity, and therefore it is easy to remember that 1 over 0 from the left will be, of course, negative infinity, and 1 over 0 from the right will be positive infinity. We now focus on the other type of infinite limits, namely those that give us the end behavior of a function. We're going to try to determine the limit as x approaches negative infinity of a function f of x, in our case 1 over x, and the limit as x approaches positive infinity of 1 over x, which in essence tells us what happens with the graph at the end, namely towards negative infinity and positive infinity. So looking at this particular graph, we observe that as x approaches negative infinity, as I travel on the curve and the x values are decreasing without bound, they're getting closer and closer to negative infinity, what happens with the corresponding heights? They are approaching the value of 1. And similarly, as x approaches now positive infinity, so if I travel on the curve of the function towards positive infinity, we notice that the heights of the graph are also approaching 0. And for that reason, we can write that the limit as x approaches negative infinity of 1 over x is 0, and the limit as x approaches positive infinity also of 1 over x happens to also equal to 0. We denote this behavior by saying that the graph of function 1 over x has a so-called horizontal asymptote. Namely, we notice that the behavior of the function is restricted towards the end by this horizontal asymptote, by this horizontal line going through the origin. Namely, you notice how the function values are getting closer and closer towards this particular line, towards negative infinity and positive infinity. So we write that this function has a so-called horizontal asymptote, and the equation for this asymptote is y equals to 0. Namely, the equation here is determined by the coordinate that is fixed, namely the height, the y coordinate is fixed as I move left or right on this particular line. This horizontal asymptote again restricts the behavior of the function towards the ends, namely towards positive and negative infinity. Therefore, we say that the end behavior of any function is given to us by the limit towards positive and negative infinity of the function. Similarly to what we had for the other limits, we're going to have a shorthand notation, an abuse of notation for the forms that we can obtain from here. So here we're going to say that 1 over, the limit is at negative infinity, so negative infinity equals to the value of 0. And similarly, that 1 over positive infinity equals to the value of 0. So in some sense, it makes, at least for this particular form here, if you have one pizza and you start dividing it amongst more and more and more people, eventually nobody gets any pizza. So this is another way to try to intuitively remember this form. So what we're going to use from what we've learned about the function 1 over x are the following forms, which are going to be very, very useful in computing other limits. Namely, to synthesize, we had the 1 over 0 from the left, right? Division by 0 gives us this explosion to plus or minus infinity. So in this case, the approaching 0 through negative values will produce the value of negative infinity, and 1 over 0 from the right will produce the value of positive infinity. These will give us the explosion near the vertical asymptotes towards plus or minus infinity. And on the other hand, talking about the end behavior, the horizontal asymptotes, we have the one form, whether we divide 1 by positive or negative infinity, in both cases we will obtain the value of 0.